All right, welcome. Today we're diving into a really fascinating challenge, one that I've spent a lot of my career on. A tiny car's very big problem. We're talking about thermal management in micro-EVs. Now you might think, small car, small problem, but you'd be surprised. Getting this right is an incredibly high-stakes game of balancing safety, performance, and of course, rock-bottom cost.
So why is this so tough? It's a great question, and it really comes down to one word: constraints. In these little cars, you have literally no extra space to play with. Your budget is squeezed down to the very last cent, and you're working with a small battery where every single watt of energy is absolutely precious. You get this wrong, and you've got an unsafe car, or a car with terrible range, or one that's just too expensive to sell. But if you nail it, well, that's how you win.
This quote from our engineering brief just hits the nail on the head. It really is a chess match. There's no single perfect move. It's all about making a series of really smart trade-offs. The solution I'm going to walk you through today is a strategic hybrid system, and it's designed to do exactly that: balance all these competing demands. Okay, first things first. Before we can do any clever engineering, we have to understand the rulebook. These are the non-negotiables. Around the world, safety and environmental regulations have become incredibly strict, and they set very hard boundaries on what we can and cannot do. Now take a look at this. You can see how different regions focus on different things. Europe, for example, is really tough on the chemicals used in air conditioning. North America is obsessed with how fast you can clear a frozen windshield. But the real game changer, the one that rewrites our entire strategy, is a new safety rule coming out of China, which is, of course, the biggest EV market on the planet.
And here it is, 2 hours. That's the new benchmark. A new Chinese standard mandates that if a battery has a catastrophic failure, what we call a thermal runaway event, it absolutely cannot catch fire or explode for a full 2 hours. Now, the old rule, it just required a 5-minute warning. This one change, this shift from 5 minutes to 2 hours, effectively makes the simple, cheap air cooling systems used in most micro-EVs obsolete. They're just not safe enough anymore.
Meanwhile, over in Europe, the challenges are different, but they're just as tough. First, environmental laws dictate that we have to use a specific, more expensive refrigerant in the AC. And second, there are those really strict defrosting rules. This means the car has to have a pretty powerful heater, which, as you can imagine, is a huge energy drain on a small battery, especially in the dead of winter.
Okay, so with those rules in mind, how are other companies solving this puzzle? The best way to find out is to reverse engineer the market. And when you do that, you see two main philosophies emerge. One is just extreme cost-cutting, no matter the trade-off. And the other is a much smarter, more strategic approach to efficiency. Let's start with the undisputed sales king, the Wuling Mini EV. Its strategy is, well, ruthless simplicity. The battery is just cooled by air flowing over it. No pumps, no liquid. It is dirt cheap. But, and this is a big but, it means you can't fast charge the car, and it really struggles in very hot or very cold weather. And most importantly, there is no way this design can pass that new 2-hour safety test.
Now for a great comparison, look at these two different takes on minimalism. You've got the Citroën Ami, which is just radical. It doesn't even have an air conditioner. Then you have the Toyota C+pod. It's also minimalist, but it's way more strategic. They keep the features customers want, but find these really clever, super efficient ways to implement them.
And the Toyota's secret weapon really boils down to this number: 100 watts. That's about all the power it takes for a heated seat to make the driver feel warm and comfortable. Compare that to a typical air heater, which can pull over 1,500 watts trying to heat up the entire cabin. It's just a genius move to save a massive amount of battery energy in the winter.
And one final piece of intel from the market comes from the Microlino. This gives us our golden power point. Its 1.8 kilowatt heater seems to be the perfect size. It's just powerful enough to meet those tough European defrosting rules we talked about, while still keeping the cabin comfortable. This gives us a really solid target for our own design.
So where does all this analysis leave us? When you look at the new global rules and you see what the competition is doing, the conclusion is crystal clear. A simple, passive, air-cooled battery system just won't cut it anymore. Not if you want a car that's safe, capable, and globally compliant. The only viable path forward is a more advanced hybrid liquid cooling architecture.
So this is the architecture we're recommending: a liquid-cooled battery pack paired with a high-voltage PTC cabin heater. And PTC just refers to a standard, reliable type of electric heater. This setup really gives us the best of both worlds. The liquid cooling is powerful enough to handle that new 2-hour safety requirement and unlock fast charging. And the PTC heater is a proven, cost-effective way to heat the cabin.
So how does this actually work? You can think of it as 3 interconnected fluid loops. The first loop is dedicated to the battery, circulating coolant through a cold plate to keep the cells at their ideal temperature. The second loop cools the electric motor and its electronics, and the third loop, well, that's essentially the AC system, which can send cold refrigerant to the cabin or, and this is key, to a chiller that cools the liquid in the battery loop. It's all integrated.
Now, you might be thinking, why go through all this trouble and expense? This slide lays out the trade-off perfectly. Yes, passive air cooling is cheaper up front, but look at what you give up. Only liquid cooling can meet that non-negotiable 2-hour safety rule. And it's the only way to deliver the fast charging speeds that, frankly, customers are starting to expect, even in a small, affordable car.
Okay, so we have our architecture, our blueprint. The next step is making it real. This is where we get into the details, selecting the right components and, just as importantly, programming smart control software to make the whole system sing.
There are 3 component decisions that are absolutely critical. First, we need an efficient, high-voltage PTC heater. Second, we must use an electronic expansion valve, or EEV, for the AC system. It allows for much finer control and boosts efficiency. And finally, the AC compressor has to be incredibly quiet. Remember, in a silent EV, there's no engine noise to mask a buzzing compressor. You hear everything.
But listen, the hardware is only half the battle. The software, the control strategies, that's where the real magic happens. This allows for brilliant things like waste heat recovery. We can actually capture heat coming off the electric motor and use it to warm the battery in the winter, for free! Or preconditioning, where the car uses cheap power from the grid to get the cabin and battery to the perfect temperature before you unplug and start your drive. And this chart right here shows you exactly why that software is so critical. Just running that simple heater in the winter can cut your driving range by 30 to 50%. It is the single biggest energy consumer on the vehicle in cold weather. By using a smart strategy like waste heat recovery, we're directly attacking the biggest energy hog and saving that precious battery range. So what's next? What's the action plan? It's a clear 3-step process. First, we simulate. We build a computer model to verify our heater sizing. At the same time, we test. We get in the lab with our battery supplier to prove our liquid cooling system can meet that 2-hour safety rule. Once that data's solid, we source. We issue a formal request to suppliers with our detailed specifications and begin the process of bringing this system to life.
Which really leaves us with a final thought to chew on. You know, as the mechanical parts of electric cars get simpler, the real competitive battleground is shifting. It's moving to these complex, invisible systems. So, is mastering something like thermal management, getting that balance of safety, efficiency, and cost just right, is that the new secret to winning the EV race? I think it just might be.